Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at something called accuracy and precision and how it relates to some data we may have collected or some data sets. So sometimes in class we do this lab where we determine the diameter of a piece of copper wire or the thickness of aluminum foil, and we collect data on that. So usually I would have 6 lab groups. Each lab group would find the diameter of copper wire, and each one would find the thickness of aluminum foil, and we would record our data as a class. So here's some sample data that I've collected in previous years. So you can take a second and copy that down. And what we're going to do is take a look at this data, analyze it in terms of accuracy and precision. Okay, so you can pause the video, copy these down, and we'll get started. All right. So the first thing we want to look at in evaluating the reliability of our results is to see, did we use the most precise instrument? So, the first question, are my instruments precise? If we have a choice of instruments to use, we want to make sure we have the one that is taken to the greatest precision, right? So examples are, if you could use either a beaker or a graduated cylinder, right? A graduated cylinder is designed to measure volume relatively accurately, right? A beaker is just for a rough amount. So a beaker, if you fill it up to the 50 milliliter line, you're getting roughly 50 milliliters. It might be like 40, 50, or 60. They're not very accurate. For your graduated cylinder, they're meant to measure volume. So if you have a graduated cylinder filled up to the 50 mark, you're pretty sure it's really close to 50. Maybe it's 49.9, 50.1, something like that. So you want to make sure you choose that instrument. If you have an option of different rulers, you want to have one with more markings, so it's more precise. You don't want to use a ruler that only has every 10 marked. You'd rather use one that has every 0.1 marked instead. Okay, so did we choose the most precise instrument possible? Could I repeat my results? Can I do the same experiment over and over and over again and get relatively similar results? So how do we test that? We want to always perform at least 3 trials. Okay, so if you could do 3 trials, and if you have results that are relatively similar after those 3 trials, usually it's an okay place to stop. But the more trials, the better. So when you're doing an example like this, say we were doing that lab that I just referenced on the previous slide, you want to vary the sample size in each trial if possible. So when you guys were figuring out the copper wire and the aluminum foil, the diameter and the thickness, use different size pieces, okay? Whether you use a 2-inch long piece of copper wire or a 4-inch long piece of copper wire, the diameter should be the same, right? Same thing with the aluminum foil. If you use a tiny square or a big square, the diameter or the thickness should be the same. If you're trying to find the density of something, density is an intensive property, so density of water. You could use various amounts of water, and you should get the same density at the end. Okay? So you want to always vary your sample size if possible. Sometimes it's not possible to, but if it is possible, that's something that you definitely want to do. If you do 3 trials or more and the results are all over the place, it's time to reevaluate your procedure or the experiment that you're performing. So what do you do then when you're all done? You take the 3 trials or more that you did, and you take your answer from all of those and you average them together. That's called your experimental answer. That's a really important vocab term to know here. So experimental error is simply the average of your trials. So sometimes students are like, well, I have 5 trials here. Which one do I pick? Well, none of them. You average the 5 together, and that gives you your experimental answer for the lab. So do I have good precision is something else we want to ask ourselves. And precision is how close together the results of each trial are. So I mentioned on the previous slide, you want to do at least 3 trials and have your results of all 3 be relatively precise. So that means you are consistent, and that means your procedure that you're performing is repeatable. So you're able to do the same procedure over and over again and get similar results. Good precision is usually a good sign of good accuracy, but not always. So I have this image here on the screen where you have these 5 points. I mean, obviously they're very precise, okay? Precision is how close together the results are. They're very close together here, but they're definitely not accurate. Okay, so you can't have an experiment where you're very precise but inaccurate. But usually, if you're very precise, that's a step in the right direction, right? The goal is to be precise and accurate, not precise and inaccurate, obviously. Okay, sometimes you can take a look at precision just by looking at two data sets and just kind of looking at the numbers that you're given here and seeing which one has the better precision. So take a second and look at these two experiments, A and B, 3 trials each. Which data set has the better precision? Okay, figure out which one has the better precision, think about why, and then we'll go over it in a second. Okay, so if you're taking a look at these, experiment A versus experiment B, trial 1, 2, and 3, you have a range here of 7.36 through 7.58. And for experiment B, you're going from 7.12 with your lowest value, and your highest value is 7.75. So I'd say experiment A definitely has the better precision. It has a smaller range of data compared to experiment B. All right, so that's pretty easy to look at and figure out. Sometimes those too close to tell, and you're looking at your data sets, you're like, oh, I can't really tell that all the numbers are relatively close together. If that happens, then you want to do something called average deviation. It's a calculation that you're going to perform. So average deviation is a measure of your precision. So we need to know that. Okay, so if I ask you what could you do to actually measure the precision of your data or measure your precision of an experiment, you would have to answer average deviation and know how to do that. So here are your steps. Okay, we'll go through them on the next slide for an example. Find the experimental answer by averaging your trials. Find out how far off each trial is from that experimental answer. Okay, that's your deviation, and then average those numbers. So if you know what deviation means, deviation just means like how far off you are. Okay, so what's your deviation from your experimental answer, and then average them. Average your deviations. Average deviation. Okay, let's take a look at it. So you do an experiment, 3 trials. You're finding the density of lithium. So you have 0.602, 0.504, and 0.613. First thing you need to do is find your experimental answer. That's your average. Average them together, you get 0.573. Okay, 3 sig figs in all of these. Okay, so 3 sig figs in your average. Next thing you want to do is find your deviation. The deviation is going to be an absolute value. Okay, so for trial 1, we have 0.602 minus 0.573. What's the deviation from your average, from your experimental answer? You get 0.029. It's a subtraction problem. Okay, so you have 3 decimal places, 3 decimal places, 3 decimal places. Okay, I know this has 3 sig figs, 3 sig figs. That only has 2, but because we're subtracting, you go off of number of decimal places. So you get 0.029. Easy. Next one, you have 0.504 minus 0.573. Notice how your answer comes out to 0.069, and that looks like it should be a negative number. But again, the deviation is just how far off you are. It doesn't matter in what direction. So you're off by 0.069 in the negative direction, no big deal, okay? I just want to know how far off the results are from the average. Okay, again, 3 decimal places. Last one, 0.613 minus 0.573 gives you 0.040, again, 3 decimal places. These are your 3 deviations, okay? So you want to do that, figure those out, and now we want to find our average deviation. Average those 3 numbers together, and you get 0.046. 2 sig figs, 2 sig figs, 2 sig figs. Answer goes to 2 sig figs. So the average deviation here is not bad, right? It's 0.046. I mean, the ideal average deviation would be 0, right? That means every trial gave you the same exact answer. You know, the density of lithium is a specific number, so it'd be nice to get the same number every time, but there's error involved, which we saw in some previous lessons. So with all that error taken into account as you do an experiment, you're going to have some sort of deviation from your average. Okay, so average deviation here is pretty good. 0.046 grams per milliliter. All these, the deviation should have a unit here, gram per milliliter. So you wouldn't have to put it in your data table every time. Okay, so now what you're going to do is calculate the average deviation for either the aluminum or copper group that you copy down on the second slide of this presentation. So I'll tell you which one that you're going to find the average deviation for. You'll figure it out, and then we'll go from there. Okay. The last thing we're going to do here is determine accuracy. So, do you have good accuracy? Accuracy is how close your results are to the accepted answer. So we did, we've measured accuracy before. in some previous labs that we've done. So here's our formal lesson on that, if you want to call it that. Your accepted answer is sometimes found in literature or easily researched. So you can find the accepted answer pretty easily if something has an accepted answer. So the previous slide, the density of lithium, you could find that by just Googling it or looking it up. So our goal is to be precise and accurate. So that's letter A here, this first bullseye. We already looked at precise but inaccurate, which is letter B. And here we have imprecise, so that our data points are spread over a wide range, and it's inaccurate because we're not near the target. Okay, so the goal here is precise and accurate, but these are what some other variations of precision and accuracy do look like. So how do we measure accuracy? We measure it with something called percent error. So it's how close our results are to the accepted answer, and it's not applicable in situations where you don't know the accepted answer. So maybe something is being looked at for the first time, some, I don't know, mystery substance or whatever, and you're trying to find the density of that. And you don't know what it's supposed to be. So you've no way to determine your percent error because there's no accepted value. Most of the stuff we do in class will have some accepted values so we can measure our accuracy. Here's our formula. You need to have this one memorized. We've used it in a couple labs already throughout the course. So important, it's experimental minus accepted in your numerator. This is an absolute value sign here. So absolute value of experimental minus accepted. So whatever this comes out to, it's going to be positive divided by your accepted. So the accepted is what is either given to you or you can easily look up, and your experimental is the average of your trials. So we already talked about your experimental answer from earlier. Okay, so subtract the 2, take the absolute value, divide by the accepted. Make sure you have units written in here as you do it, times 100, and you're good to go. Your percent error should be, again, as close to 0 as possible. It'd be great to have 0% error where you have the same experimental answer from your lab as the literature says as your accepted value. Usually not going to happen, but that's the goal. So, whatever you did for the precision data, where you had to find the average deviation, if you were the copper group or the aluminum group, you'll do the same thing here. So calculate the percent error for your assigned set of data. So the accepted value for the thickness of aluminum foil is 0.0240 millimeters, and the accepted value for the diameter of the copper wire that we used in the lab is 0.115 centimeters. So take a minute and use these accepted values. This accuracy is a little bit quicker because you don't have to do all that subtraction like you did for average deviation. Go through, find out what your percent error is, and we'll go from there. Okay. Last bit of this lesson here, just on some good experimental practices. So sometimes you go through a lab and things are going great, and then you come up with some data point that is really far off from your other ones. You're like, oh, that doesn't look good at all. What do I do with this? So this goes, this discussion here is about rejection of data. What do you do if you have a data point that looks wrong? Well, you can never just throw it out because it looks wrong. You can't just erase it or delete it from your computer and pretend it never happened. Okay, it's not allowed. So never throw out a data point because it looks wrong. There is a way to get rid of it, but you have to go through a process. If a known error occurs, so say some blunder did occur in lab where you spilled something, you realize you measured something wrong, like you forgot to hit the tare button. So some example like that, like you used a wrong chemical, you didn't read the procedure the right way. Yeah, get rid of that data point, okay, and do that part of the experiment over again. That's allowed, okay, so those are known errors or blunders that occur in the lab. But if you follow the procedure as is, and there are no known blunders or mistakes, then you can't just get rid of a data point because it looks bad and it bothers you, okay? So a Q-test has to be performed on a data point that looks like it's wrong. When you take statistics, you'll learn all about the Q-test. There are lots of other tests that mean various things in statistics, but we're only going to look at the Q-test very quickly. It'll statistically verify if the data point is most likely bad and should be thrown out. You can't do this for 5 data points that look bad. Okay, you can do it for 1. Only 1 data point can be discarded using this test. So here's your formula for it. You want to find the Q value. Okay, the Q value is your outlier, the data point that looks wrong, okay, minus the value closest to it. Okay, so you look at your big data set, find the one that looks wrong, find the number closest to it, absolute value. Okay, subtract the 2. Divide it by the range, which is your highest value minus your lowest value. That's going to give you a Q value. Okay, and this is the quick and easy method here. An explanation. When you take statistics, at some point you will go into this a little bit more detail, I'm sure. Once you find your Q value, you want to look up something called a QC value on a table of Q critical values for the number of trials that you performed. So at the back of your statistics book, you're going to have a huge like appendix or something where you have all these numbers for like Q values. I don't even know what other letters there are. There's a ton of them. I remember it was a long time since I took statistics in college. But you're going to have all these values in the back that you compare values that you calculate to those. Okay. What you want to do is see if your Q value is bigger or smaller than the critical Q value that you look up in your textbook. So they're all given to you, or they would be given to you on a test or anything like that. There's no need to memorize any of that stuff. If your value is bigger than the critical value, your data point can be discarded with 90% confidence. Okay, so that's important here. In the back of your book, you'll see 90% confidence, maybe 95% confidence, maybe 99% confidence. So it depends on how confident you want to be that you can get rid of that data point. The critical Q values are different based on your confidence level. Okay, so if you want to be really sure, like if you want to be 95% confident, you can get rid of that data point. You want to compare it to the QC values at 95% confidence. So let's take a look at how we do this on a quick data set here. So here's a lab you performed, finding the melting point of gallium. You have 4 values there. Take a look at that. Does one of them look like it's an outlier to you? You have 28.7, 23.5, 29.1, 28.2. I look at those, I'm like, well, it looks like data point number 2 would be like one I want to erase. Okay, pretend that never happened. Can't just get rid of it though, because my experiment went like it should. There were no blunders or anything, so I should perform a Q test to see if I can get rid of that. So I want to calculate the Q value. Here it is. I should have units here, so 23.5 Celsius is my outlier, minus the number closest to it, which is 28.2, divided by my range, 29.1 minus 23.5. Okay, my value comes out to 0.839. That's my Q value. My critical Q value from my table is 0.76. I have that on the next slide. I'll go to that real quick. So in the back of your book, or what you're given, is 90% confidence for your Q test. Number of trials is here. Notice how it doesn't start until you have 3, which is why we want at least 3 trials. We did 4 trials there, so we want to compare it to our 4 trial number. Notice how the more trials you have, the lower the critical value becomes. So if you do 10 trials and 1 looks like it's an outlier, that's not bad, right? So it's easier to get rid of that data point. If you do 3 trials and 1 looks bad, you need a pretty high QC value to get rid of that. So we did 4 trials. QC value is 0.76. So we want to compare our value to that. And it's bigger than it. So we can be 90% confident we can throw out that data point. Okay? So we're not 100% confident. It might still be something of significance there. But we could be, like it says here, 90% confident we can get rid of that data point. All right? So what we can do, and we'll just use these values. We'll just go with 90% confidence, but just know that there are other confidence levels in your in a statistics book if you were to do this. Look at the data from the lab, and you could look at either the copper or the aluminum. And if you're on Edpuzzle, I'll probably instruct you to pick one or the other and find a data point. Look at the data that's given. Could we throw out any data point or any data in either group? So the only way to find that out is to run a Q test and see if your Q value is bigger or smaller than the critical Q value, which you guys can just use these when you do it. Okay, so you can go back to this part of the video and look at these QC values, or maybe they're even in your notes, to see if you can get rid of a data point. That really takes care of it. Okay, it's the last slide here. So relatively quick lesson, pretty easy lesson on accuracy, precision, and bad data. So you need to know how to calculate precision, which is the average deviation. You need to know how to calculate accuracy, which is percent error. You need to know which one is for which. And then for the Q-test and the Q-value, you just need to know about it. If you had to figure out if a data point could be eliminated or not, I would give you the formula for the Q-test. I would give you the confidence values at 90%. I would give you a lot of that stuff. So the only memorization here is your accuracy, which is percent error formula, and your precision, which is your average deviation process. All right? All right, guys, that takes care of it. See ya. Thanks.